Welcome to the video for pre-lecture 6. So in this lecture we're going to be discussing the difference between the explicit and implicit Euler's method. And so in the previous lecture we introduced the idea of explicit Euler, and ultimately this equation was effectively derived based on the Taylor expansion. And so we said, okay, well, we have x at t plus delta t is equal to x at t plus delta t times dx dt plus all these other terms, but for our purposes, for the explicit Euler purposes, we're going to neglect these higher order terms. And a critical aspect that we really didn't get into too fine of detail is the realization or the importance that dx dt is evaluated at time t. So what this means is that x of t plus delta t, that's our x of n plus 1, is equal to our x at t, which is our x of n, plus delta t times dx dt evaluated at time index n. So if, for instance, our dx dt was equal to x, then this would then just become x of n. But if we were to perform the Taylor expansion, instead of centering it at x at time t, we were to center it at x at time t plus delta t, we would get the following Taylor expansion with the condition that our derivatives are evaluated at our time index n plus 1. And so if we neglect the higher order terms, again, we drop down to just an equation of x of t is equal to x of t plus delta t minus delta t times dx dt at time index t plus delta t. And this then becomes our implicit Euler equation, where we rearrange and say xn plus 1 is equal to x of n plus delta t times dx dt. But now it's going to be evaluated at time index n plus 1. So a very subtle difference. The only difference being that our time index for our derivative evaluation for implicit Euler is at time index n plus 1, and for an explicit Euler, evaluated at time index n. But this small difference is going to play out in very different ways. So let's just take a look graphically at how this works. So again, our implicit Euler equation is our xn plus 1 is equal to x of n plus delta t times dx dt evaluated at time index n plus 1. And our explicit equation is x of n plus 1 is equal to x of n plus delta t times dx dt evaluated at time index n. So graphically, what this corresponds to is taking a step at a particular slope. And so for our explicit, this step is taken at our slope dx dt evaluated at t equals to 0. Versus for our implicit case, our first step is the dx dt, but now evaluated at t equals to a half. Noticing that's where we're wanting to end up at the time step of, well, I guess it's not quite 0.5, it's probably something more like 0.4 or something like that. So we take our first step at these different slopes, and we can see that our results are starting to diverge away from our analytic solution. And in this case, our implicit form is overestimating the value, and our explicit form is underestimating the value. So there's another difference between these two, though. If we were to say that dx dt is equal to some function f of x and t, then our implicit equation becomes x sub n plus delta t times f of x sub n plus 1 and t of n plus 1. And our explicit equation becomes x sub n plus delta t times f of x sub n and t sub n. Now, an important thing to identify, though, is what are the unknowns in our equation? The unknowns are the values at time index n plus 1. So for the explicit case, we only have one unknown, and it's on the left-hand side, which means all of the information on the right-hand side is known, and we can take those values, plug those into the equation, and then move forward easily. Implicit Euler comes with potentially unknowns on the right-hand side. And so for that reason, this may require isolating our x of n plus 1 value so that we have an equation that we can use to determine what the next state should be. So let's take a look at how this plays out for a particular example. So for dx dt is equal to x plus t, that's our f of x and t. For our implicit equation, that's going to be x of n plus 1 is equal to x of n plus delta t times the derivative dx dt evaluated at time index n plus 1. So that'll be xn plus 1 here plus tn plus 1. For our explicit equation, it will be similar. Xn plus 1 is equal to x sub n plus delta t, but now the difference being that now what's in parentheses is going to be x sub n plus t sub n. So again, highlighting our unknowns. For our explicit Euler equation, no problem. We have all the information at time index n. We can take that, plug that into our equation to get our value at n plus 1. But for our implicit equation, we have to rearrange things slightly. So this can be rearranged by pulling our term here to the left-hand side. And so that'll give us 1 minus delta t times xn plus 1 is equal to x sub n plus delta t times t of n plus 1. Now I haven't highlighted t of n plus 1 as an unknown because we know that t of n plus 1 is equal to t of n plus delta t. But we'll leave it as t of n plus 1 because that's sort of a simplicity of our notation. So then we can divide across and isolate x of n plus 1 is equal to x sub n plus delta t times t of n plus 1 divided by 1 minus delta t. And so this would be the equation then that we could use when trying to code up how we would march forward in time. Now, if you had multiple equations or if it was a higher order ODE, you would simply have to rearrange more equations to isolate each one of the unknowns for their own equation. Now you can imagine there are instances where maybe it's not so straightforward to rearrange. What do we do in those cases? Well, we'll discuss in a couple lectures the option of, instead of rearranging the implicit Euler equation, to simply perform an iterative approach to get a converged result. So why would we go through all this effort? Why would we ever want to use the implicit Euler versus the explicit Euler? Well, what you'll find, and what we'll show probably either in the next lecture or in our homework, is that it turns out that the implicit Euler equation tends to provide a more stable solution. That there are instances where our explicit Euler will actually diverge away from our analytic solution, even if the method is being performed properly. The implicit Euler tends not to be as subjected to those instabilities. But again, this will be material we cover later in